Okay, so our next section we're doing is electrochemistry. So we talked about oxidation and reduction last week. So we're going to continue on this. And your next exam, I believe, is all just electrochemistry. So it's a pretty big chapter. And so we're going to be spending some time on this. Now, for electrochemistry, it's really important that we know our oxidations and reductions. So remember, I'm just going to write this here: lose electrons, oxidation, gain electrons, reduced, right? Leo goes grr. That's going to be kind of our governing piece, and we're going to be using that again and again and again and again. So when we balance this, the first thing we do is we separate our variables. So remember, if we do our oxidation states, anything by itself is 0, and monatomic ions are just whatever their charge is, monatomic ion, anything by itself. So if you look at the aluminum here, our aluminum went from a 0 to a +3. And remember, electrons are negative, so this became more positive, meaning it lost electrons, right? So therefore, it is oxidized. And if we look at copper, I probably should not put oxidized right there. Put it right there. Copper, it went from a +2 to a 0, so it became more negative. It gained electrons, so therefore it was reduced. And so when we do the balancing of our oxidation reduction reactions, this is a really simple one. You're going to see some really difficult ones, but if you just follow these 5 steps, you can balance any oxidation reduction reaction. So find our oxidation state, determine who's oxidized, reduced, and we split our variables. So I like to treat it a little bit like math. So aluminum goes to aluminum 3+, and copper 2+ goes to copper. So we split our variables. Our next step is balance everything but H and O. Well, it's balanced, so we get to skip this one. Our next step, add water to balance O's. Don't have any waters. Add H's to balance H's. If it's in base, well, this is not in base. So this one so far is pretty easy. Now we have to balance the charges. And so when we balance the charges, this whole side is a 0, this side is a 3+. All we can do is add electrons. So we need to add electrons to make sure that each side is the same. And so we'll add 3 electrons to this side. So now this whole side is a 0, and this whole side is a 0. We look at our copper, this side is a +2, this side is a 0. Again, we need them to be equal. So we'll add 2 electrons to this side. So now this side is 0 and this side is 0, right? So that's what we mean by this step right here. Balance half reactions by charge, right? Adjust the electrons.
I had a question.
Yeah, go ahead.
So like, let's say for aluminum, let's say there was 2 different charges, like let's say instead of like the plain Al is like Al2+, and the other one is Al3+. Do we have to make it equal 0 on both sides?
Yep.
Oh, okay, makes sense.
Yeah, and there we're gonna see, I don't know if we'll see them today, but we'll definitely see some of them where you actually have like 2 iodines in one step. Yeah, we definitely won't see that one today, but we will next week or the week after. You'll see like there'll be like multiple ions, like iodine will be in 3 different compounds. But yeah, so each side, no matter what the charge is, it's the sides that have to be equal.
Okay.
Yeah, great question. Okay, so now in our final reaction, we can't have any electrons, so we need to get rid of our electrons. So if we multiply this one by 2 and this one by 3, both of our electrons will be 6 and we'll all be set, right? So I'm just going to do this down here. So I'll multiply that one by 2 and this one by 3, did it on both sides. So 2 aluminums goes to 2 aluminum, 3 pluses plus 6 electrons. And then we have 6 electrons plus 3C I just want to make sure I have enough room. 6 electrons plus 3 Cu. Oh, the whole thing. My pen. 6 electrons plus 3 Cu. 2 pluses. There we go. Makes 3 Cus. Got it. All right. Then we add. And our electrons had better fall out. And so when we do this, we end up with 2 aluminums plus 3 Cu, 2 pluses, makes 2 Al, 3 pluses plus 3 Cus. And I don't have the states in here, but obviously the aluminum and the copper by themselves are solid, and the ones with the charges are aqueous. So this is going to be like a balanced redox reaction. So we're going to do this, and this one, by the way, is an acid, although you can't really tell, but I'm going to show you, we're going to do our next one. It's going to be in base. And so, by the way, stop me, ask questions through this if you get stuck, because when you're doing oxidation reduction reactions, if you get lost right here, nothing makes sense back here because you can't go back and figure out what happened, right? Yesterday, on Monday, I tried to do it in separate colors so you could see it, but it's really hard if you get stuck up here to figure out anything that happens down here. So just go, hey, wait, how did you get that again? And I can go back.
Can I ask a question then?
Yeah. Go ahead.
Why did you switch the 2 and the 3? Like for aluminum, why is it that you multiplied it by 2 and the copper by 3?
Great question. Okay, so that is this step right here. Whoops. Let me just get rid of this. This is this part right here where we have to balance the electrons with the half reactions. And so you can see right here, this one has 3 electrons on this side, and this one has 2 electrons. So if we just added these reactions right here, we would have the electrons in the final adding of them. We can't have that. There can't be any electrons in the net ionic equation. We have to get rid of them. So in order to get rid of them,
the 6 electrons when you end up.
Exactly. That's how we get rid of them, because we need a 6 here and a 6 here, so we can cross them off.
Oh, because if you didn't do that, then it would still be like a 3 and a 2 on both sides.
Exactly. And when we finish, we can't have any electrons.
And like, let's say you had 3 reactions. Will all those 3 reactions have to
You'll only have 2.
Okay. Sorry.
I promise.
Okay.
You only have 2. That I guarantee. They won't all look like this like simple, but they'll only be 2. I promise that. Okay. Any other questions on this one before we go to one that's got more fun in it? Okay. So now I'm going to show you how to do it in acidic solution and in basic solution. So in lab, you guys are doing these redox reactions all the time, right? We're always doing these, and it says like, oh, make sure it's acidic or make sure it's basic, right? And so if you're wondering like, oh, am I doing a redox reaction? Just look at your oxidation states. If they change, you've got a redox reaction. Like I said, almost all of them in lab are not almost all of them, but a lot of them are redox reactions. So if you look at the oxidation states, right? And this is a -1, and look at, there it is, 0. This is definitely a redox reaction, right? That'll tell you that right there. If you see any change in an oxidation state, it's a redox reaction. So remember our rules for assigning oxidation states: group 1 + 1, group 2 + 2, fluorine's always -1. So those 3 are non-changeable. Group 1 + 1, group 2 + 2, fluorine's always -1. Those are non-negotiables. And then oxygen is usually -2, right? Hydrogen's usually +1. But again, those can change. So now we don't have any reason to believe that oxygen's not -2 here. So if oxygen's a -2, right, and it has to equal -1, just a little baby bit of algebra here, that means that this manganese must be a +7. Oxygen's a -2, there's 2 of them, so manganese must be a +4 here. So we can see we've got, and in any of these oxidation reactions, one person, well, not one, there's an oxidation reaction and then there's a reduction reaction, right? So in order for there to be oxidation, there must be reduction. In order for reduction, there must be oxidation, right? Because in oxidation, one atom, right, lose electrons oxidized. So if we look here, who got oxidized here? So here's our two choices, iodine or manganese. So which one got oxidized? This is my question for the chat for you guys. Who's oxidized? This is going to become really important to see soon. So whoever was oxidized lost electrons. Remember, and it's gain electrons reduced. Yeah. Iodine, right? Iodine went from a -1 to a 0, right? And then if we look at manganese, manganese went from a +7 to a +4, right? Right, so our manganese, actually, I think I'll go back. It'll be easier to see. Our manganese became more negative, so it gained electrons, +7 to 4, right? So it's more negative. I know it's positive. So our manganese was reduced. I'm just going to point to this one because it's closer. And our iodine was oxidized. So the iodine lost electrons. The reason that oxidation and reduction always have to go together, because if iodine loses electrons, the electrons have to go somewhere, right? They can't just be. And so the electrons go to manganese. So if iodine loses the electrons, manganese has to gain the electrons.
I have a question.
Uh-huh.
I'm still confused on the part where how did you get the +7 and the +4?
Okay, so that comes from the oxidation states. So the rules again, group 1's +1, group 2's +2, oxygen's usually -2, fluorine's always -1. And if the oxidation states, if it's a monatomic ion, it's just the same as the ion. If it's by itself, it's just a 0. Since oxygen here is a -2, and this whole thing has to equal -1, and then oxygen's...
Do they always have to equal -1?
It's whatever the charge is. So you see here on this one, in order to make this true, it has to be a +7, but this one has no charge. So this one equals 0.
0, oh, okay.
And so in order to make this one complete, this one has to be a +4.
Oh, let me write that down. That way I can remember it.
Yeah, not a problem. So yeah, these oxidation states, it's going to be the most important thing that like our basis and doing this whole entire section is assigning the oxidation states, because you have to know who's oxidized and who's reduced. And sometimes it's kind of hard to see, and you'll whichever way your brain works, it's often easier for people to see the oxidations or the reductions. Like for me, my brain sees the reductions really easy, so then I know the other one must be oxidized, right? So I can see the gaining of electrons. It's harder to see when they lose them for some reason in my brain, but it's in a lot of times I always tell people it's kind of the opposite of what you think, because electrons are negatively charged.
Yeah, okay, that makes more sense now. I was confused on the first time you were doing it. I was like, wait, what? Okay, I get it now. Thank you.
Yeah, perfect. And again, if you guys have questions anywhere on these, because I'm telling you, electrochemistry completely builds on itself, and no one here has ever seen it before. So make sure you ask questions if you get stuck anywhere. So we're going to balance this in basic solution. So I'm going to do this. I'll try to do it neatly, and then I actually have it all nice on my PowerPoint in just a minute. So if we do this, we have I minus goes to I2. And I'm not going to put the states in because that will just hurt my hand too much. And then we have MnO4 minus goes to MnO2. And so we separate our variables. The next step, balance all but H and O. So I'm going to say balance. I should have just copied this over. Let me just see if I can really fast, actually, instead of writing all of this over again. So balance all but H and O. And then, I know I just put it right here. Then you're going to balance. The computer doesn't want to work right now. Ah, there we go. I'm just going to grab this so I don't have to rewrite it. Oh, that's too big. I'm just looking for a small version of this to write. There, that's what I want. There's nowhere neat for me to do this, so I'm just going to put it right here. Okay. I had to put it on the next slide. It's the only place it would fit. And now it's not even showing it. Ugh, okay. All right. So I'm just going to tell you the statement so I don't have to write it all. So your first thing is balance all but H and O. So we're going to add a 2 here. And I'll just keep going back. There you go. So balance all but H and O. Next, balance O's with water, H's with hydrogens. O's with water, H's with hydrogens. So we have our O's. 4 oxygens over here, 2 oxygens over here. So plus 2 waters. Now we have 4 oxygens here and we have 4 oxygens here. But now our next step is balance H with H pluses. Well, now we have 4 H's, so we have to add 4 H pluses over here. Okay, so this right now, I'm going to leave this one an acidic solution, and I'm going to show you how to do it in basic solution in just a second. Okay, so our next step, we have to balance the charges. Okay, so if we look here, this side's a -2. Let me just get rid of these so they're not confusing. This side's a 0, right? So we can only balance with electrons. That's 2 electrons. This side is a 4 plus a -1. So this side's a 3 and this side's a 0. There's a lot of 2s and 3s this time, right? I should make this +3. And so we'll add 3 electrons to this side. So now this side is also a 0. The next step, multiply to make the electrons the same on both sides. So we need the electrons to fall out. So we're going to multiply this one by 3 and this one by 2. So both of our electrons are 6. Ends up being the same as we just did. So this is 6. I'm just going to rewrite this here. Try to write this nicely for you. So it's 6 I minuses. I'm going to try and keep this more symmetrical. 6 I minuses. Just want to make sure that we know that that's different. Goes to 3 I2s plus 6 electrons. Our next one is going to be 6 electrons plus 2 times 4, 8 hydrogens plus 2 MnO4s goes to 2 MnO2s plus 4 waters. Oof. Next step, add. I'll come right back. So we just balanced the electrons. Now we're adding the half reactions. So that's our next step. We add them. Our electrons had better fall out. So then we're left with 8 H pluses plus 2 MnO4s. I think I lost a minus there. Plus 6 I minuses goes to 3 I2s plus 2 MnO2s plus 4 waters. And this is in acid. And again, how do you know it's an acid? Those H pluses. So this is balanced in acid. And again, the elements are going to balance and the charges are going to balance, right? So you need to check that both element and the charges balance, right? So if we look here, if we look at our charge, right? Here's an 8 plus, here's a -2, a -6. So this all equals 0, and this is all 0. So our charges are the same. By the way, they don't both need to be 0. They could be both like -20 or +15. As long as they're the same, it doesn't matter. They just happen to be 0. Okay, so questions on this one, because now I'm going to do the same thing, but I'm going to do it in a base. There's only one tiny step for the base. Questions on this one? I wonder if I can add something here for you. Aha. Okay. We're going to do the same thing. We're just going to do this one in base. I got this to work. Okay, so this is going to be the exact same thing, but this time we're going to do it in a base. So what I want you to see here, this is the only difference. That's it. That's the only difference if it says in base. So again, we're going to do the exact same equation, just this time we're going to do it in base. So we already know, whoa, I minus goes to I2, right? MnO4 minus goes to MnO2. By the way, if you can do this faster than me, absolutely do it. Okay, same step here. Balance all but H and O's. Did that one. Here we are, add water for O's. Add H's to balance H's. So you can see this right now is exactly the same, and I am so gonna run out of room. Okay, so now here's where the new step is. So our new step is, if it's in base, you're going to neutralize the H pluses with OH minuses. So what we're going to do is we're going to add OH to neutralize our H pluses. So let me show you. I'm just going to write this exact equation right here so you can see this a little bit better. So I'm going to add 4 OH minuses. And whatever you do to one side, right, it has to be the same. So plus 4 OH minuses. Okay, and this is the only new step here, right? So that's our only new step. So now if you look at H plus OH is water, so this is 4 waters. So now we have 4 waters on one side. You can see we have 2 waters on this side. So you can simplify this now or later, whichever one makes you happier. I like to simplify it sooner than later. Actually, we'll just leave it this time. We'll just leave it as 4 waters and we'll just simplify it later. But it doesn't matter where you simplify this, it's gonna work the same no matter what. Okay, so now I'm just gonna rewrite this with water. So it's 4 waters plus MnO4 minus goes to MnO2 plus 2 waters plus 4 OH minuses. Okay, so now we're at this piece right here. balance the charge by adding electrons. And so it just always ends up the same. So if we look at this one here, we have 2 electrons. Just wondering where I'm going to put this. So on this side, we have a -4, right? And this is a -1. So we have to add 3 electrons. I can fit this in here. 3 electrons here. So both sides are -4. And multiply this one by 3, multiply this one by 2, so those electrons fall out again. So I'm just going to rewrite this one down here. And so now we're going to get rid of those electrons. 6 I minuses goes to 3 I2s plus 6 electrons. And then I'm just gonna rewrite that over towards the middle so I have a little bit more room so I can keep this symmetrical. 6 I minuses goes to 3 I2s plus 6 electrons. And then our next one's going to be 6 electrons plus 2 times 4, right? 8 waters plus 2 MnO4 minuses goes to 2 MnO2s plus 4 waters plus 8 OH minuses. And so now we have to simplify our waters, right? So, and this becomes a 4. So our final is going to be now we're going to add these. This is going to be really long. 6, so I'm going to add these right now. 6 I minus plus our electrons fall out, 4 waters.
Oh yeah, okay, that's what I was going to ask.
2 MnO4 minuses. By the way, if you see me make, these are so easy to make mistakes on, right? You have to like keep all your ducks in a row and then some. 3 I2s plus 2 MnO2s plus 8 OH minuses. And how do you know it's in base in the end? That's how you know. And again, we check our charges better match. So I find your elements obviously have to match, right? So if you look, 6 I's, check they need to match. I find it easier if your charges are off, it's easy to see, right? Because here's 6, here's right -6, -2. So this whole side is a -8. This whole side is a -8. Our charges balance. So we should be good. Charges are kind of a dead giveaway if you've done it wrong. And you can see, so our balanced net ionic equation is this, right? It's so much fun, so much fun. Okay, so I'm going to show you this whole thing again, but I'm going to show you neater separated by step. So if you got stuck anywhere here, hopefully this will clear it up. Okay. By the way, oh, here's our 1 in acid. I kept this. I'm going to have to delete this because I wrote it over another thing. But here's our 1 in acid. So you can see it's very similar. 2 MnO4s, 2 MnO2s, 2 MnO4s, 2 MnO2s. The really only difference is the hydroxides in the water. And the water's over here. That's the only difference. Okay. Unfortunately, I have to erase that because the rest of this is under here. Okay, so we found out we split our variables. That's what we did. We separated our reactions into oxidation and reduction. The next thing we did, oh, that's what I was trying to add earlier. There's where it went. The next thing we did, balance everything but H and O. So we added a 2 in front of our I. That's our next step. Our next step is to balance O's with water. 4 oxygens here, 2 oxygens here. So we're going to have to add 2 waters. So now we have 4 waters on each side. So now we have 2 O's and 2 O's, 4 O's. Our O's are balanced. But now our hydrogens are not balanced, right? We have 4 hydrogens over here, so we need to add 4 H pluses over here. You balance hydrogens with H pluses. So we added our 4 hydrogens over here. Now here's the step that's not an acid. So because this says in basic solution, we balance or we neutralize our H's by adding OHs. Whatever you do to one side, you have to do to the other side. So you add 4 OHs to one side to get rid of these. You have to add 4 OHs to the other side. So here we are adding our 4 OHs to each side. Then you can see this is 4 waters. If you want to leave it as H's and OHs, that's fine. You can do that. I'm going to leave it as waters though. In the end, you're going to have to simplify it. Again, where you simplify doesn't matter. In the middle or the end, you're going to need to simplify it eventually. All right, so now we have this. So again, we could simplify this here. So you can see how there's 4 waters here and 2 waters here. So we can just simplify that here and then just change this to a 2. I mean, again, wherever you want to simplify your H's, it's fine with me. This time I've simplified it here. It's going to work out both ways. Okay, so now here's our 2 reactions. We have this reaction and this reaction. So I'm just going to have both of those on the next side. Now we have to balance our electrons. This is a -2, this is a 0, so we need to add 2 electrons here. This is a 0, this is a -4 because of that. So not a 0, -1. I keep missing these charges here, right? It's a -1. So we're going to add 3 electrons to this side. I think I have that here. Oh yeah, way better. Oh look, I almost did that perfect. And so now this side's a -4 and this side's a -4. This side's a -2, this side's a -2. Our charges are now balanced. Okay, next step, get rid of these. We need these to go away. So we're going to multiply this one by 3 and this one by 2 because we need them to go away. And so here we are. Our oxidation reaction is right here. We multiplied it by 3. There's our reduction. We multiplied it by 2. And the last step we do is we add them. And remember, the reason we multiplied this is because we need these electrons to fall out. Right? This one's in the products, this one's in the reactants, so they're going to fall out. Not the best way I did that, but close. So then we add them. And here's what we got. I'm pretty sure this is exactly what we got, right? Our charges were right, so the chance of us getting it correct is pretty high. So here is our balanced net ionic reaction. Again, check your elements, check your charge, right? I always check the charge first because usually if there's a mistake, you can see it in the charges right away. The charges are just instantly show you if you've made a mistake. Okay, are you ready to try one on your own? Because after this one, we're going to actually start applying these. So you need to be able to see them and understand how to balance them on your own. It really is a system. So separate your variables, balance all but H and O, balance O's with water, balance H with hydrogens, cancel your charges or make each side equal using electrons, and then multiply to get rid of the electrons and add. Okay, here you go. I want you to try this one. So I'm going to give you a couple minutes, whether you're watching this now or watching this later, try to balance this one. See how far you're going to get. I'm going to give you a few minutes to do this because there's a lot to it and you have your notes. So make sure you go back and look at the rules and see if you can do this. We're going to balance this in a basic solution, right? So this is in a basic solution. So try this and then we're going to go over it in a few minutes. How are we doing? Do you need some more time or are we ready? More time? Okay, I'll give you a couple more minutes and then we'll go through it. right, let's try it. First thing, assign those oxidation states. And anytime throughout this, if you get stuck on anything or have any questions, just please let me know and I can clarify. So we can see our iodine went from a -1 to a 0. So it became less negative, more positive, how you want to say that. So it's oxidized. Our chromium went from a +6 to a +3. So it became more negative, meaning it gained electrons. So it was reduced. Then we're going to separate them based on oxidation reduction, right? So separate our variables, I's in one, CR's in the other. Next piece. First, balance everything but H and O. So just put a 2 in front of our iodine. Nothing really has to happen with our chromium, right? Our next step, balance O with water. So we're going to have to add 4 waters here. So we added 4 waters. Well, then that messed it up. Now we've got 8 hydrogens. So we have to add 8 hydrogens to the next step. Here's the little additional piece we need to do right here. It's in basic solution, so we're going to add OHs to neutralize the hydrogens. So we're going to add 8 OHs here to this side and 8 OHs to the other side. There it is. I was like, where'd it go? So we add 8 OHs, 8 OHs. Now remember, these 8 OHs, that's the same as saying 8 waters. Right? So that's 8 waters. So I'm just going to combine that into 8 waters. Okay, then you can simplify your waters here, you can simplify them later. I like to simplify them earlier. So if I have 8 waters here, 4 waters here, those just go away, and now I have 4 waters total. Oh, look, I did that for you here. Very nice. So we have 4 waters. So now our 2 equations are our oxidation and our reduction equation, right? So these are our 2 equations we have. Everyone good on this part so far?
Can you go back to the last slide?
The whole, like...
Yeah, that one.
Uh-huh.
Okay, thank you.
Good? Okay. Any questions before we go to the next part? The next part's the electrons. Good on this? Okay. So we have our 2 equations. Now we have to balance our electrons. This side's a -2, so I'm going to add 2 electrons to this side. So now they're both -2s, right? This side is a +3 and a -8. This side's a -2. So 3 electrons means they'll be equal. So I added 3 electrons. I don't know why every single one I chose you this time has a 2 and a 3. It's not like that. It just must be coincidence the way I chose these. It's not always 2s and 3s, I promise. Okay, so now we need to multiply to get rid of our electrons. So we're going to multiply the top one by 3, the bottom one by 2. When we do that, this is what we should have, right? And you can see our electrons will indeed fall out. And then we finally add our equations. And this should be our balanced equation. If we check everything, indeed, our charges do balance and our elements do balance. Okay, questions on this if you did not get this? Any questions on this at all? Everyone's good on this? Okay, so now we're going to start using it. So again, what we did, we just worked on balancing our redox reactions. It's really a system. So once you learn the system, it should be pretty down pat. Now we're going to talk about what an oxidation reduction reaction is and how it works. Okay, so hold on one second. My daughter. Okay, so oxidation reduction reactions are the movement of electrons, right? And so electrons, like electricity, electrons are negatively charged. They move away from the negative towards the positive. Hold on one second. I'm busy in lecture, can't talk. She's very demanding. Okay, so when we talk about electric current, we're talking about the movement of electrons, and electrons will always go from the negative to the positive. Think of it like water in a stream, right? Water in a stream goes from like higher to lower. It's the exact same thing as it is with electrons, right? They're always going to go from negative towards the positive. So when we talk about redox reactions in current, it involves the transfer of electrons from one substance to another. So our oxidation, whoever is being oxidized is losing electrons, and whoever is being reduced is gaining electrons. So it's always a movement of electrons from one place to another. Someone loses, the other one gains. Therefore, the redox reactions have the potential to generate an electric current, because electric current is just the movement of electrons. So what we're now going to talk about is we're going to talk about the current created by redox reactions. So in order to use the current, so I'm going to show you a redox reaction that doesn't use the current, then I'm going to show you how we can actually use the current of oxidation reduction reactions. And so what we're going to do is we're going to look at this reaction. So this is just a strip of zinc. So it's just zinc metal, and it's sitting in copper 2+ solution. And then you can see here, we have, this is copper, and then you can see there's going to be a zinc ions here, sitting here. So if we look at this, there's a movement of electrons. And so you can see we have, so this is zinc solid. This is copper solid, right? And so you can see our zinc, and this is just before and after. So our zinc went from a zinc solid to zinc 2+. So we went from a zinc solid to a zinc 2+. We went from a 0 oxidation state to a +2, right? So our zinc lost electrons. So if we write this as an oxidation reduction, went from Zn 2+ 2 electrons, right? It lost electrons. If we look at our copper was a 2+, and it ended up at a copper solid. So it went from copper 2+ to copper solid. And so our copper gained the electrons. So these are the same electrons. The zinc lost the electrons, hence it was oxidized, while copper gained those 2 electrons and was reduced. And this is what we mean. This is like an oxidation reduction reaction. One loses, the other one gains. And so if we look at this, what happened was, here's our zinc solid, right? And then our copper 2, our zinc solid lost the electrons, and copper 2 was like, hey, thanks for the electrons, right? Well, actually, probably it's right here. And then it became a copper atom, right? So zinc lost them, and copper was like, hey, thanks a bunch for those electrons, zinc. And zinc's like, hey, no problem. This is an oxidation reduction reaction. Now, there is a movement of electrons from the zinc, to the copper, but it's not really useful because it's all in the same container. So what we're going to do is we're going to look at how you can separate the oxidation reaction from the reduction reaction and get an actual movement of electrons. Okay, so what you're seeing here, this is an electrochemical cell. So an electrochemical cell just has an oxidation piece and a reduction piece. This is the exact same thing as this. I'm just splitting it up. And by the way, your first quiz, you're going to be drawing this. It's going to be wonderful. So what we have is here's our zinc solid. right? And then we have our copper. And then here we have zinc 2 plus, and we have copper 2 plus in our solution. All right, so now we know that you can see here our zinc wants to lose electrons, copper wants to gain electrons. So you can see our zinc solid wants to lose electrons. Like here it is losing the electrons. So it's losing the electrons, and the electrons are going towards the copper because the copper wants to gain those electrons. So we've kind of separated it out. Now, if the electrons continue to go this way, then what's going to happen is this solution is going to become very negative, right? And this one's going to become very positive, and eventually it's just going to stop. I shouldn't put the positive up here. It's become positive. So what we have is a salt bridge, and a salt bridge helps us equalize the charges, because what's going to happen is we're eventually going to hit equilibrium and it's going to stop. Well, we don't want to hit equilibrium. We want this reaction to keep going. So therefore we need to neutralize the charges. So we use a salt bridge, and usually any salt, any ionic compound, any soluble ionic compound works. In this case, we used KNO3. So what happens is the positive ion will travel to the solution here to join these negative ions to keep it electrically neutral. This one, the electrons continually kept leaving, is going to be left positive, right? So the negative ion will travel in the salt bridge to neutralize this reaction. So we need a salt bridge to overcome our equilibrium, right? And normally, if we didn't have COVID, you would actually get to set up a salt, you would actually get to set this up. You take the salt bridge out, reaction stops. Put the salt bridge in, reaction keeps going. It's instantaneous. All right, so now, again, if we look at this, here's our zinc, right? This is our oxidation. I'm just gonna say oxidation. Here's our reduction. Ooh. You can see our oxidation here of our zinc is at our anode. So where there's oxidation, there's an anode, and where there's reduction, we call that the cathode. Remember the first thing I told you is, right, Leo goes Gur. That does not look like an O. Leo goes Gur. Well, Leo, the red cat, goes Gur. Because reduction happens at the cathode. Reduction, cathode. Okay, so Leo, the red cat, goes Gur. Lose electrons, oxidize. So you can see the electrons are traveling this way, away from our zinc. Our zinc is losing electrons. So lose electrons, oxidize. Our zinc is oxidized. Our copper is gaining the electrons, so therefore it is reduced, gain, electrons reduced, and reduction happens at the cathode, right? So reduction happens at the cathode. And you can see here at our cathode, we're Cu2 plus going to copper. At our anode, our oxidation, we're zinc going to zinc 2 plus. So we have a solid here that's turning into an aqueous. So this is going to continually lose mass. This is going to continually lose mass, where this one is going from an aqueous to a solid. This one is going to gain mass. So eventually, if we could get it to go far enough, our zinc would totally disappear and we would have a ton of copper over here. Right? And this is an electrochemical cell. And what we're doing is we're just maximizing and we're just using the movement of the electrons. And remember, electrons, the movement of electrons, that is electricity. So if you did attach a voltmeter or a light bulb, you would have electricity in this case. So this is actually electric current moving from our anode to our cathode. Okay, so now let's just talk, these things here, these are called half cells. So this is an oxidation half cell, and this is a reduction half cell. So that's what we call these. We call these half cells, these electrochemical cells. And remember at the very beginning when we did our balancing our oxidation reduction reactions, right? We separated the oxidation reaction from the reduction reaction. Here we are applying that exact same thing. So for our electrochemical cells, our half cells, the electrons flow through a wire with an ion through a solution, and that's what creates our electric circuit. And so we need an electrode, something that can transfer the electrons. So an anode and a cathode, those are what we call our electrodes. It can also be graphite, which we're going to talk about not today, but next week. But it's usually metals, but it also can be graphite. So, and again, it requires an ion exchange between the half cells of the system, and this is going to be what we call an electrolyte. Now, if you remember from 219, an electrolyte is anything that comes apart into ions in solution, right? So like NaCl is an electrolyte because it comes apart into ions into solution. So in this case, in the cell that we have here, this was our electrolyte. Right, so our salt bridge contains an electrolyte to keep the two solutions neutral, otherwise the reaction stops. So these are our electrochemical cells. So we've got anodes, cathodes, we have to connect it with some way the electrons can transfer, and we also need to have a salt bridge that can keep both of the solutions electrically neutral. Okay. So now let's talk more about our anode. Remember, our anode, lose electrons, oxidation. This is where oxidation occurs. The anions are attracted to it. I'm going to keep coming back and forth here. I'm going to just erase some of my chicken scratches here. The anions are attracted to it because it continually is losing its negative charge, right? It's losing its negative charge through these electrons, leaving the solution itself positive. And so the anions are attracted to it so they can make a neutral solution. That's what that statement means. In a battery, it's connected to the positive end of the battery. In an electrolytic cell, which we're going to talk about electrolytic, voltaic, and other cells, but not today. It also loses weight, right? Because remember, the reason it's losing weight is because we're going from a solid to an aqueous. So our solid, this electrode right here, is continually becoming our aqueous solution. So it's losing weight. A cathode, red cat, right? Goes grr. Leo the red cat goes grr, right? Cathode, reduction happens at the cathode, right? Grr, gain, electrons reduce. This is where reduction occurs. The cations are attracted to it. What do I mean by that? In our salt bridge, right, electrons are continually coming over here, making this solution negative, so the cations will be attracted to it to make this a neutral solution. Right, so the cations are attracted to it. It's connected to the negative end in an electrolytic cell, and it gains weight. So if you've ever heard of electroplating, like if you ever had like any kind of a jewelry that's a plated jewelry, this is what they do. They electroplate it. And we're actually going to talk about this. So for example, if you have like a platinum ring, but it's really shiny, platinum's not a very shiny metal, they usually coat it with white gold. How do they do that? Electroplating, right? Or if you have like something that's just gold plated, electroplating. It's actually really fun to do, these electroplating. Okay, so let's review our electrolytic cells really quickly. All right, so now, what do we have? So we have our salt bridge that completes our circuit and maintains a balanced charge, right? So we have our, just to review again, we're going from a 0 to a +2. So therefore it's losing electrons. So we have our zinc and our zinc 2 plus, so it's losing electrons. And here we are, we gave it a conduit to lose the electrons. This is going from a +2 to a 0, so it's gaining the electrons. Here is our copper. I'm trying to make it 2 here. Here's our copper gaining electrons, right? So, and again, this is going to increase mass because the electrons are going from here and creating more of our copper, versus here, it's the opposite. It's going from zinc to zinc 2 plus, right? This is our oxidation. This is our reduction. This is our cathode. Well, I have it written right there. So in your very first quiz, I literally ask you to draw this. I give you an electrochemical reaction, just like I did in the very first, the balancing chemical reaction, just like we did. And I ask you to draw this whole thing. So how do you do it? First, you decide who's oxidized, who's reduced. Your electroplates are metals. So this has to be zinc because it's a metal. This one has to be copper because it's a metal. I'm just going to rewrite this. And again, the reason I'm not writing these nitrates here is because those are spectator items, not really important in our reaction. Then you need to know the direction of the electrons. The directions of the electrons always go from the anode to the cathode. Why? Because the anode is the oxidation. They always lose electrons. The anode is always losing electrons. The cathode is where reduction happens. The reduction is always gaining electrons. So here's the direction of our electrons. So they're going this way. And then you need to have a salt bridge. And you have to note which ion is going in what direction. Well, the potassium, or the positive ion, is always going to go towards the reduction. Why? Because the electrons are going the same direction, and they need to neutralize each other here in that solution. The anion is going to go towards the anode, or towards the oxidation, because the electrons are continually leaving the anode, leaving the solution to positive. So the nitrate will, or the negative ion will go over here to balance the solution out, right? So that's basically what your electrochemical cell will look like. So now when we're looking at this, we have current. So current is just the number of electrons that are flowing through the system. So if you take physics ever, you might talk about amps, right? This is electrons. So when we're talking about 1 amp of a current, that's 1 coulomb of charge. And so 1 amp, this is how many electrons are actually going through, right? It's a lot of electrons. So the electrode surface area dictates the number of electrons that can flow. So this is why if you have like a smaller battery, let's just use like batteries, if you have a AAA battery, that's going to be less current than maybe a D battery, right? I would say power, but again, we're not going to do physics. Okay. Now, voltage is different. So current is just the flow of the electrons, right? It's the number of electrons that flow through the system. That's current. Voltage is looking at the potential difference. And so the difference in the potential energy of the reactants and products, that's what we're talking about, a voltage, a volt. So 1 volt is 1 joule of energy per coulomb of charge. I promise you, you will not have to do math with these. This is very physicsy. We're just going to talk about it in qualitative terms. When you get to physics, you will do all the calculations with it. So the voltage, what we have here, we talk about what's needed to drive the electrons through a circuit. So the amount of force that's making the electrons move through a wire, that's what we call our electromotive force, or our EMF, right? So that's kind of our background about our current and our voltage. Now we're going to talk about how we use this. We're really going to talk about voltage just for a second. So when we talk about what's called our cell potential, which is measuring the voltage, The difference in the potential energy between the anode and the cathode is what we call the cell potential. And it depends on how easily our anode oxidizes and our cathode reduces, right? So it just depends on how easy, again, our oxidizing agent reduced and our reducing agent oxidized. Remember this one? So we're saying that all in one statement. So the cell potential depends on the relative ease in which the oxidizing agent is reduced. Remember, oxidizing agent is the one that's reduced at the cathode, and the reducing agent is oxidized at the anode. Remember, red cat. So under standard conditions, our standard EMF, which we note as E cell, is, again, here's this little thing right here. What does that mean? 25 degrees Celsius, 1 atmosphere, 1 molar concentration, right? So again, that's standard means 25 degrees Celsius, 1 atmosphere, and 1 molar. So a lot of times what's going to happen on your exams and your quiz, and you're going to be like, you didn't tell me the concentration. But this will be there. This means 1 molar, right? We don't really change our temperatures or our pressures here, but we are going to be changing our concentrations, right? So if you see that little standard sign, that means your concentration is 1 molar. Okay, so now, how do we write what I just showed you in our electrochemical cells? So what you have is, so to write these cells, you have your electrode, and then this is like the line between your 2 electrodes, and then your electrolyte, this is your solid, this is your aqueous. This means salt bridge, right? This is salt bridge. That's what that means there, salt bridge. And we call these phase barriers. Right? So these single phase barriers, these are just the difference. Now, you can't have multiples in the same phase, and we'll talk about how to do that later. And then our salt bridge, that's just our double line. So let's look at the exact same thing we just looked at. I'm going to go back. Right. Just going to go back to the one we were just on. So if we look at this, our electrode is zinc. The electrolyte is zinc 2+. So I'm looking, and my oxidation always goes on this side. Then I have a salt bridge. Here's my salt bridge. And then I have my electrolyte and my electrode. And this is how, so like, for example, if I gave you just this, just that, you should be able to draw this entire thing, right? Just from this little baby, this little baby notation, you're going to be able, by the end of next week, you'll be able to draw this entire thing just right off the top of your head, which is actually quite fun. Okay, so I think we'll stop there because your brains have got to hurt.